The topic of this video, or the topics rather, will include the atomic spectra of the hydrogen atom and hydrogen-like ions. And then we're going to talk about that first because it's closely related to our most recent topic of the energy levels of the hydrogen atom. And then we'll move on to looking at the shapes of the wave functions. Okay, so in the previous lecture we talked about the energy levels of the hydrogen atom, and we talked a little bit about classical turning point and defined something called the Bohr radius and the Rydberg constant. And so we're going to use those concepts to talk a little bit about what we expect in the atomic spectra. And first of all, what do I mean by atomic spectra? There you can set up an electrical discharge tube so this would be a cathode ray tube in which electrical energy ionizes, first dissociates hydrogen H2 into ions or into individual atoms, and then ionizes some of them, and there's a series of processes of relaxation processes for the atoms in the excited state, and we'll talk about that in just a second. So there's an electrical discharge tube. Basically you've got some gas in a tube, and you have some electrodes and some, when you apply a high voltage and strike sort of an arc in this, you generate a plasma, and the plasma is a complex sort of mixture of atoms in the excited state and ions and free electrons. And so this plasma has kind of this dynamic equilibrium where electrons can recombine with protons to make hydrogen atoms in the excited state, and then the hydrogen atoms in the excited state can give off photons to relax in energy to lower energy states, eventually to the ground state, and then the hydrogen atom presumably gets excited either by collision with other atoms or other ions, or by sort of electrical excitation of the sort of current running through the cathode ray tube. So basically current runs through this tube, putting energy into the system and putting hydrogen atoms into excited states. And then the atoms can lose energy, emitting photons, and also some heat gets released by these tubes. And you may have seen one of these discharge tubes in a previous physics course in a demonstration. So electrons recombine with protons. You get atoms in the excited state. And we can call that H star, and that gives you photons and H in the ground state. And again, this is a dynamic equilibrium where then that hydrogen atom can get re-excited because energy is being put into the system. electrical energy. Okay, and so essentially there's this cascade breaking down this process a little bit more. So you have an H plus and an electron. They can recombine to form H star in some excited state, N, let's say, and it can lose energy, right? So this is an excited state. It's not a stable state. The more So what the system tends to do is lose energy via photon and drop down to a lower energy state. We'll call it M, and so on. And where N and M are quantum numbers, and it can keep doing that until we have H in the N equals 1 state. And so the discharge spectrum is a series of bright lines that you can see with say a diffraction grating. And this is something that, again, maybe even in a high school or middle school science class, you may have had the opportunity to look at a hydrogen atom or other atom emission spectrum through a diffraction grating. You see a series of sharp lines. And so this is one way of looking at the process. Another way of looking at the process is in terms of an energy level diagram. So the sort of lowest energy state of the system is N equals 1. So let's set that as our sort of baseline here. And then, of course, above that, you're going to have other energy levels. N equals 2, N equals 3, 4, so on. And so you can have, and because this is kind of a random process, a lot of stuff going on, recombining, emitting, and so on, so you end up with essentially a soup of all of the different excited electronic states of the hydrogen atom. And so you can have, say, a transition between N equals 2 and N equals 1, and that's going to give rise to a photon that's going to be equal to the difference in the energy between those two states. You can also go directly from N equals 3 to N equals 1. Now it may not be as intense a line, but it will be there. It may not be as intense for a couple of reasons. One is the sort of rate or the probability per unit time of emitting a photon from the N equals 3 state to take you down to the N equals 2 state. And you can have, of course, going from N equals 4 and so on. So you can have a series of, you end up with a series of lines that I'm going to group together here. This isn't the only series of lines, but this is a series of lines that we call the Lyman series. And basically it has to do with emission, where the final state is N equals 1. The final state of the transition. So a transition between two energy levels where the upper level is N equals 2 or higher, and the lower level is N equals 1. So we can say NF equals 1. Similarly, there's another series where again, there's nothing quantum mechanically that says we can't relax, instead of going all the way down to the ground state, relax from, say, n equals 3 to n equals 2, n equals 4 to n equals 2, and so on. And that is called the Paschen series. And so both of these series of lines, or sorry, that's the Balmer series. And then Paschen is n equals 3 as the final state. And this is just a categorization scheme. There's going to be all these lines, and they sort of get grouped together, although there's some overlap between these series of lines if you run the numbers. But those are the line spectra. And what else to say about that? Oh, yeah. So one of the things, of course, that led to the development of the quantum theory was this Rydberg formula, which we now have a physical justification for. And, oh yeah, and NF equals 2. And the Rydberg formula tells us that delta E is equal to h nu. So the photon energy is equal to the energy difference between these two levels, and that energy level difference is Rydberg constant times z squared over 1 over nf squared minus 1 over ni squared, where nf and ni are the initial and final states of the transition, and ni is greater than nf. Now that's for atomic emission. There's a similar process where if you have thermally excited hot H atoms in a hot plasma, like in the vicinity of the sun, then what you're going to see is you're going to see this continuum spectrum of the sun with a bunch of dark lines superimposed on top of it. So you'll see this nice rainbow with little dropouts, little dark lines in the rainbow when you disperse it with a diffraction grating or prism or prisms, and in which case the definitions of initial and final state are a little different in that case because you have a continuum of light and you have H atoms in various states, and they can go from one state to the next, absorbing a photon in the process, so going from a lower state to a higher state. And so that's kind of like the mirror image of this process, and that occurs as well in the solar spectrum. But anyways, in any case, it follows this Rydberg type formula, where the Rydberg formula, the Rydberg constant is the constant that we previously derived for the energy levels that describes the sort of set of constants that in the formula for the energy levels of the hydrogen atom. Okay, so now that we've discussed energy levels and something a little bit related to the energy levels, which is the line spectrum, now let's move on to the wave function the radial parts of the wave functions and the angular parts of the wave functions. And first of all, it's good to recall that our wave functions in this system, they're going to be a function of so far 3 quantum numbers, n, l, and m sub l. So they're going to have be characterized by 3 quantum numbers, and of course they are functions that are given in spherical polar coordinates. They're going to be functions of r, theta, and phi. And we previously supposed, but haven't really proved yet, although we're inching close to that, that this is because we pick this spherical polar coordinates that allows us to apply the principle of separation of variables, where we break up this wave function into a product of 2 simpler functions, and these 2 simpler functions are solutions to a simpler Hamiltonian. And we saw already the radial Hamiltonian, where the angular parts are replaced with the centrifugal potential. And so we end up with a one-dimensional Schrodinger equation that can be solved. And of course, we're getting close to looking at the solutions. Anyways, it's a product of R and L. This is a solution to the radial part of the Schrodinger equation. And it's just a function of R. And a product of that and these spherical harmonics, the YLM, which are functions of theta and phi. And of course, you recall the spherical harmonics, or the Legendre polynomials. These are, or sometimes just called the YLMs. These are also solutions to the rigid rotor problem. So we got to recycle them to take care of the rotational motion of electron around a nucleus. And of course, so it's a product of those 2 functions. And the quantum numbers are the principal quantum number n. That starts at 1. So those are all the possible values for n. And then the L quantum number, its minimum value is 0, and it goes up to n minus 1. Okay, and the L quantum number has to do with the shape of the orbital. L equals 0 corresponds to S-type orbitals, the sort of spherical orbitals. L equals 1 corresponds to P-type orbitals. L equals 2, D-type orbitals. And you're at least somewhat familiar with the shapes of most of those orbitals, and we'll talk more about those in a minute. And as you may recall from the Aufbau principle lectures in general chemistry and perhaps in physics courses, that there's no such thing as, say, a 1p electronic state. For n equals 2, you start to get, in that corresponds to the second row of the periodic table, you start to get these p orbitals, and then in the next row, you start to get d orbitals as well, and this is related to the overall shape of the periodic table. And it comes from the fact that even though there's a separation of variables, the angular momentum shows up in the this L angular momentum quantum number or orbital quantum number affects the centrifugal potential such that centrifugal potential is steep enough for n equals 1 where there's no bound state allowed. And so so the separation of variables isn't complete, but it's sort of lessens the impact such that the effect of angular momentum on the Hamiltonian is to limit sort of which combinations of n and L are allowed. And for other systems where there's some kind of barrier, you can have, such as things like solvated electrons, you can have 1p electrons in a solvated electron. But for electrons orbiting a nucleus in vacuum, you can't. Okay, so and then the third quantum number is the ML quantum number, or the sometimes called the magnetic quantum number or the azimuthal quantum number, and that ranges from -L to L. And so there are only certain sets of quantum numbers that are allowed. You can't have n equals 1, L equals 2. You can't have L equals 0, ML equals 1. So, you know, there are these, this is, in order to properly follow this scheme, you have to implement those rules. Okay. Now, before I write expressions for the radial part of the wave functions, let's define a dimensionless radius. We'll call it sigma, where we take ZR and divide it by A0, where A0 is the Bohr radius. Which we defined previously, and it's related to a bunch of constants, and it is 0.529 angstroms. And so when we take the radius and divide it by the Bohr radius, that gives us a simplified expression for the radial part of the wave function, and it also allows us to define wave functions for different values of z, where z is the nuclear charge. In terms of multiples of the electron charge. Basically, the atomic number. Okay, so our 1s type orbital is going to be given by, or wave function is R10. And it has some constants out front, 1 over square root of pi, z over a aught, to the 3/2. Okay, but don't worry too much about that. Those are just constants out front that help to normal. Those are just part of the normalization constant, so those don't really affect the shape of the function. They're just what pops out when you normalize it. The important part is the the actual shape of the function is given by e to the minus sigma. So it's a very actually simple wave function. So our radial Hamiltonian, if you may recall, looked somewhat complicated. You took a ddr and you multiply by r squared, and then take the derivative again, and then divide by r squared, things like that. So it's a rather complicated set of differential operations that are involved in the Hamiltonian. But nevertheless, yeah, this ends up being a solution, and this can be verified. And that would be a perfectly reasonable exercise to work through on the homework. So that might show up in the homework. And so we have a simple sort of exponential shaped function, and we'll talk about the shape of it shortly. R20 is our next wave function that we're going to talk about, and it has a slightly different normalization constant out front. Still has z over a aught to the 3/2. Oops. And we have a 1 over 4 roots of 2 pi. Again, that's just the normalization constant. You really shouldn't focus on that too much, as the more important part is the parts that contain sigma. Those really tell us what the shape is. And it's the shape that ends up affecting integrals and telling us sort of what the overall shape of the orbitals are, and things like that. So that's what we should key on, not the sort of cabbage out front that we just need to sort of take care of the accounting and make sure that that our probability density integrates to 1. That's basically what the normalization constant's for, right? Okay, anyway, so this 2 minus sigma times, times e to the minus sigma over 2. And R21 is 1 over 4 roots of 2 pi z over a aught to the 3/2 sigma times e to the minus sigma over 2. Okay, so these are going to have somewhat related shapes. Some features will be similar. And now let's look at plotting these. Of course, we could just plug them into a plotting program. And you end up with, so when we plot these, we end up with something that looks like this for R10. We have as a function of little r. The value of this starts off, it's an exponential function. So if we plug in sigma equals 0, that's going to give us a value of 1. And so we would just, so e to the minus 0 is 1. And then we would just have these constants. And so it's a sort of simple exponential decay looking function, e to the minus sigma. And yeah, we can plot it as a function of r, or we can one thing that's a useful way to characterize an exponential decay is the 1 over e point. In other words, when that's telling you roughly, how quickly it decays. You can think of it as if this were a kinetics problem, it would be the lifetime, which is related to the half-life. It's not exactly the half-life, but there's a simple algebraic relationship between the 1 over e point and the half-life. So, but this is not a decay in time, it's a decay in space, right? So that 1 over e point, that's where the argument inside the exponent is equal to -1. And so that corresponds to, if we drop a line, a vertical line from that point, so there would be 1 over e would be 1 over e of the initial value, so that'd be about, and e is about 2.7, so this is about, roughly 60% from the peak, 60% drop from the peak. That's the 1 over e point. And then where that occurs, so the value at which that occurs is, again, is at about 30% of the initial peak value at r, or sigma equals 0. And when you drop down and look at the r-axis, that's going to be occurring at sigma, when r is equal to sigma. And then that's when, or sorry, let me back up. That's where sigma equals 1. Okay, and yeah, not at r equals sigma, at sigma equals 1. Okay, so then r20, so in other words, that 1 over e point is going to happen at sigma equals 1, and since sigma is equal to zr over a aught, it's going to be at a value of zr over a aught equals 1, and so you can do a little math there to find out where the 1 over e point is. Now for the next one, for r20, if we plug in at sigma equals 0, we're going to have this first part in parentheses here, this 2 minus sigma, that's going to be equal to 2, and then of course sigma is going to be 0, so the exponential function would have a value of 1, and so it's going to start off with some positive value, and then it's going to go through 0 roughly at, it's not going to be a straight line, it's going to be some kind of curve, but it's going to look a little bit like a straight line, and it's going to go through 0 at sigma equals 2. And then it's going to go negative for a while, and then it's going to decay off exponentially at large values of r or sigma. Yeah, let's just call that axis sigma there. It makes it simpler. And so that's roughly what this looks like. So there's this R20 has a node at sigma equals 2. And this is in line with our previous experience, where we see that wave functions that have higher quantum numbers and that are higher in energy have more nodes. And so the R10 has no nodes, or has a node at sigma equals infinity, and R20 has a node at sigma equals 2. And R20 corresponds to the to the 2s. Now let's look at what the 2p type wave function looks like. That's R21. And that is just sigma times e to the minus sigma over 2. And so that is looks a little bit like this, right? So there's this starts off increasing, starts off at 0, then it increases for a while, goes through maximum, and then decays exponentially after that. And this also has a node, but the node is actually, it's not so much in the radial part, because at r equals 0 we can't really have a node in the radial part of the wave function. The node is really in the angular parts, as we'll see later on. And I didn't show the functional form, but for our 3,0, which would be a 3s wave function, it's going to look kind of like R20, except it's going to cross. There's going to be two nodes, so it's going to dip down. It's going to be a higher order polynomial in sigma, and it's going to look like that, although that's not quite right, because it's actually going to extend further out in space, because it's larger than that one. So anyway, so that's going to have two nodes, one here and here, and that would be for 3s. Again, two nodes, and then goes through a maximum, and then decays off exponentially at large r or large sigma. Okay, so far so good. So that's what the radial function looks like, but there's a problem. There's a couple of problems. One of the problems is that some of these wave functions, we look at R20 and R21, or sorry, R10 and R30. All of these are exponential functions that don't vanish at the origin, that don't vanish at r equals 0 or sigma equals 0. So there may be a problem here. Now, why is that a problem? It's a problem because now previously, let's see, it's a problem because at r equals 0, the Coulomb potential goes to minus infinity. And so there's always, we have to be extra careful when there's an infinity involved. Now, in the case of the particle in a box, we had an infinite potential barrier at the edges of the box. And we were able to sort of avoid that because the probability density was 0 at the edges of the box. In fact, that gave us our boundary conditions, which define the confinement and give us the energy levels of the system. So we could avoid it by having the wave function e be equal to 0. But here the wave function is not 0 at r equals 0 for some of these, right? For the various s-like wave functions, and so this it looks like if an electron has some probability of being at the nucleus, it would be in an infinite potential well, meaning that it would take an infinite force for it to escape and leave the nucleus, and and that, so essentially you would have a collapse of the system. That's the problem when you have an infinity or some kind of singularity in the system. There can either be a collapse or some sort of ionization of the system, one or the other. And so this is this is a little bit like the UV catastrophe problem of uh, of applying Maxwell's equations to a particle moving around in an orbit. I won't go into that in detail, but this is kind of like a catastrophe problem. So is there a contradiction? Is there a problem here? How is it resolved? So it turns out that these are stable wave function orbits. There is no collapse, and um, the issue is something called the Jacobian, or the differential volume factor. And you may recall that that d tau in spherical polar coordinates r squared dr sine theta d theta d phi. And if we integrate over theta and phi, that gives us d tau. If we integrate over theta and phi and just have the radial part, that's going to give us 4 pi r squared dr. And so it turns out that there's this r squared dr, and so anytime we would try to, say, calculate an expectation value for the potential in a particular region of the system, say, let's say very close to the nucleus, and if we include this r squared and the wave function and the potential, so the r squared ends up canceling the 1 over r in the potential, and you end up with a non-infinite expectation value for the potential. So that's one way to look at it. Another way to look at it is that essentially the probability of being very, very close to the nucleus. So mathematically that works is, okay, well, the r squared cancels the 1 over r. But the way to think about it in terms of probability is that the d tau is the volume of a spherical shell. So the area of a sphere is 4 pi r squared, and the thickness of the shell would be dr. And so the volume of an infinitesimal spherical shell is going to be 4 pi r squared dr, and that's what we get for our d tau. So this has the effect of as r gets smaller and smaller, of course the area of the sphere is smaller and smaller, and so if our probability is is proportional to the volume element, then we would expect the probability of the particle being at some very, very small value of r is going to vanish. And so this helps us to avoid this problem, this apparent singularity, and so then we often, but it introduces another complication in that if we want to plot the radial distribution or the radial probability, we have to include this volume element. And so our differential probability is going to be equal to some function, say we'll call it P and L times dr. And then and we know probability is related to the R and L, but we also have to take into account the Jacobian, and so it ends up being R and L squared times 4 pi r squared times dr. So typically when we plot these wave functions, when we plot a radial distribution function, we're going to include this r squared factor, this little r squared factor, because that's going to give us a better representation of the probability of finding the electron at some very, very small radius. That probability is going to be very small because the volume of space that's very close to the nucleus is very small. Purely a volume element sort of thing. So when we do that, then we end up with, instead of our wave function having some value at r equals 0, so for P and L, let's say for probability 1s, we end up with a function that looks, it's going to start off with a value of 0, and then it's going to increase quadratically for a little while, right? Because the r squared, the little r squared kind of starts to take over until the value of r gets large enough, and then the exponential part takes over, and so it ends up looking like this. And for 2s, we end up with a curve that's going to have sort of two humps. Again, these are the radial probability curves. And for 2p, it's going to look a little similar to the 1s, but it's at a little bit larger distance. And so on. These are just rough sketches. Again, we may have some homework problems where we get a chance to plot these using a computer. Now, the other thing we need to keep track of is the angular part. And so I think this is a pretty good place to stop. So next lecture, we'll talk about the angular part, and we'll see how to relate the YLMs to the to various 2p orbital shapes that we may have some familiarity with already.